In this video, we will talk about eigenvectors in upper triangular matrices. This is our overview slide, which we'll spend about 5 minutes going over before the main part of our video, where we'll go over each topic in more detail and with examples. We will start with the topic of polynomials applied to an operator. That's a polynomial P applied to an operator T. Suppose T is a linear operator on a vector space V, and P is a polynomial over a given field F, and the polynomial P of Z is equal to A0 plus A1Z plus A2Z squared up to AM Z to the M for Z and F. Then the polynomial applied to the linear operator T is equal to A0I plus A1T plus A2T squared up to AMTM, where Tm is equal to our operator applied m times. T0 is the identity operator I, that's this I here, on V, and if T is invertible, then T to the minus m is equal to T to the minus 1, that's its inverse, m times. This next topic we have alluded to in Chapter 4 when we talked about polynomials, in our previous video when we talked about eigenvectors and eigenvalues. And that's this theorem: operators on complex vector spaces have an eigenvalue. That is, every operator on a finite dimensional non-zero complex vector space has an eigenvalue. What this formula tells us is the kth column, these are all the kth column entries, is equal to the operator T acting on the kth basis vector. So TV of K is the kth column. However, we have to express that column in terms of our new bases, V1 up to Vn. So if it's the standard bases, it's quite straightforward. If it's not the standard bases, there's a little bit of work here. Note, since this is an operator that maps from V to V, the matrices will be square, that is, they're n by n. And if no basis is specified, we can assume the standard one. With these matrices, we have one of the goals of linear algebra is, given a linear operator T on a vector space V, we want to find a matrix M of T that has as many zeros as possible. And one of these goals is the upper triangular matrix. So first we have the definition of the diagonal of a square matrix, and those are the entries along the line from the upper left corner to the bottom right corner. So here is an example of a matrix. From this upper left corner to the bottom right corner, we have these entries, these scalar entries, lambda 1, lambda 2, lambda n. And it is no coincidence that we use the same notation, the lambdas, as we did for eigenvalues, but we'll see that later. Next, we can define our upper triangular matrix. So this could be one of the goal kind of form of matrices that we want that has as many zeros as possible. So the upper triangular matrix is a matrix where all the entries below the diagonal equal to 0. We notate an upper triangular matrix this way. We have our diagonal that has different constant values on the diagonal. On the top, we have this asterisk, meaning it's kind of a wild card. We can have whatever values on this upper part of the triangle of this matrix. But this lower triangle of the matrix below the diagonal, all of these entries should be 0. And we just note that with the 1, 0 to represent this whole lower triangle. Then the question becomes, when is it possible to have an upper triangular matrix? And we have this theorem, conditions for an upper triangular matrix. Suppose T is a linear operator and V1, V2, Vn is a basis of V. Then the following are equivalent. 1, the matrix of T with respect to our bases is upper triangular. 2, T of Vj is in the span of V1, V2 up to Vj for every j between 1 and n. And then 3, the span of V1, V2 up to Vj is invariant under T for each j between 1 and n. I find this next theorem surprising, but we will prove it in the main part of our video. Over the field of complex numbers, every operator has an upper triangular matrix. So suppose V is a finite dimensional complex vector space and T is a linear operator, then T has an upper triangular matrix with respect to some basis of V. Then these last two theorems are examples of how analysis of an operator is simplified if you can choose a good basis to get an upper triangular matrix. The first one is determination of invertibility. Suppose T is a linear operator on V and it has an upper triangular matrix. Then T is invertible if and only if all entries on the diagonal of that upper triangular matrix are non-zero. And second, determination of eigenvalues from an upper triangular matrix. Suppose T, a linear operator on V, has an upper triangular matrix with respect to some basis of V. Then the eigenvalues of T are precisely the entries on the diagonal of the upper triangular matrix. So here, again, as I mentioned, there was no accident. We notate upper triangular matrices within the lambdas on the diagonal. So these last three theorems tell us over the field of complex number, every operator has an upper triangular matrix, which means a good choice of bases will give us an upper triangular matrix, and the analysis of our transformation now becomes significantly easier. We can determine the invertibility just by looking at the diagonal, and we can determine the eigenvalues just by looking at the diagonal. This concludes our overview, so we're ready to take a closer look, and we'll start with polynomials applied to an operator. So suppose T is a linear operator on a vector space V, and P is a polynomial over F, given by P of Z is equal to A0 plus A1Z plus A2Z squared up to AMZM for Z in our field F. Then our polynomial applied to our linear operator T is equal to A0I plus A1t plus A2t squared up to AM t to the m, where t to the m is our linear operator applied m times. And T0 will be the identity operator on V, and if T is invertible, then T raised to the negative m is equal to the inverse of T raised to the m. The main reason a richer theory exists for operators than for general linear maps is that operators can be raised to powers, which leads to the concept of applying this here, a polynomial, to an operator. We have this example. Suppose D is the linear operator over the polynomial space over real numbers, and D will define as the differential operator, defined by D applied to a polynomial Q is equal to Q prime, the first derivative. And suppose P is the polynomial defined by P of x is equal to 7 minus 3x plus 5x squared. What is P of D? And what is P of D on a polynomial Q? Using my definition here of a polynomial applied to a linear operator T, I now have P of D plugging in. I have my 7, and then I need my identity operator, minus 3 times D plus 5 times D squared. It's really kind of what you would intuitively expect. Now, if I apply P of D to a polynomial Q, I'm going to get 7, my identity operator on Q, minus 3, my operator D on Q, plus 5, my operator D squared on Q. And now I have 7. The identity on Q is simply Q, minus 3 times the derivative of Q, plus 5 times the derivative applied twice to Q gives us the second derivative of Q. We can also now define the product of polynomials if P and Q are polynomials over F, then PQ is a polynomial over F and is defined by PQ of Z is equal to P of Z times Q of Z for all Z and F, kind of what you would expect. We have these multiplicative properties if P and Q are in the polynomial space over a field F and T is a linear operator on V, then PQ of T is equal to P of T times Q of T, and P of T times Q of T is equal to Q of T times P of T. Also, something you expect just from what you know about functions and operators. Our next topic is existence of eigenvalues. We have this theorem that says operators on complex vector spaces have an eigenvalue. Every operator on a finite dimensional non-zero complex vector space has an eigenvalue. The proof of this theorem depends on the fundamental theorem of algebra, which we had covered in Chapter 4 about polynomials. I have it here for your reference. Every non-constant polynomial with complex coefficients has a zero. We will start here with every operator on a finite dimensional non-zero complex vector space. We'll suppose V is a complex vector space with dimension n greater than 0, and T is a linear operator on V. We're going to choose a vector V from our vector space V that's not equal to 0. If we consider now the n plus 1 vectors, V, TV, T squared V up to Tn V, we know they are not linearly independent. In other words, they're dependent because dimension is equal to n, and we have n plus 1 vectors. If they're linearly dependent, that means there exist a0, a1, an, not all zero, such that a0 v plus a1 tv plus a2 t squared v up to an t to the n v is equal to 0. In other words, there's a non-homogeneous system to the linear equation. Note that a1, a2 up to an cannot all be 0, because if they were, that would imply a0 v equals 0, and since v, we had chosen that to not be equal to 0, that would imply a0 is equal to 0, which would mean all of our coefficients were not equal to 0, but that's not possible because they're linearly dependent. We can now interpret this expression here as a polynomial applied to our operator t. We can now make these coefficients, this a0, a1, a2, an, into a polynomial. So we have our polynomial a0 plus a1z plus a2z squared up to anzn. And now this expression is our polynomial applied to our transformation t. And now that we have a polynomial, by the fundamental theorem of algebra, since we have zeros, we can factor. And we can factor this polynomial into c z minus lambda 1, z minus lambda 2, up to z minus lambda m. And this factorization was also something we had covered in Chapter 4 when we discussed polynomials. Oh, and I should note, the c over here and all these lambdas, those are complex numbers, they're scalars. And the equation here holds for all complex values z. And last, this m over here for our lambda m may or may not be equal to this n, our last a sub n zn, because our an might be equal to 0. Leaving this here for a moment, I'm going to take this equation and rewrite it down here. So I have my 0 is equal to a0 v plus a1 tv plus an t to the n v. I'm going to factor out my vector v. So I have a0 I plus a1 t plus an t to the n times my vector v, and I can do that because it's a linear transformation. And now, by this work here, we said that we can factor this part of the polynomial to see t minus lambda 1i times t minus lambda 2i up to t minus lambda mi, all times our vector v. We have this theorem from our previous video that says injectivity is equivalent to the null space equaling 0. Here, because we have a non-zero solution to the homogeneous equation, that implies that our transformation is not injective. So what we have then is one of these t minus lambda j sub I is not injective for at least one of these j's. That is, t has an eigenvalue. Our next topic is of the upper triangular matrices. We will start with this definition of a matrix of an operator m of t. So suppose t is a linear operator on a vector space V, and the vectors v1, v2 up to vn is a basis of V. The matrix of t with respect to this basis is the n by n matrix whose entries a sub jk are defined by the transformation t on the kth basis vector is equal to a sub 1k times v1, the first basis vector, up to a sub nk times vn, the nth basis vector. Essentially, what we're going to get is the kth column of our matrix vector is going to be equal to the transformation T on the kth basis vector. Also note, since this is an operator T maps from a vector space V back onto itself. So T maps from V to V. So since it's an operator, the matrices are all going to be square, n by n. And if no basis is specified, we are going to assume the standard one. We have this example: define T, a linear operator on F3 by T of xyz is equal to 2x plus y, 5y plus 3z, 8z. What is the matrix of T? Since no basis is specified, we're going to assume the standard bases. So that's E1, E2, E3, or the basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Looking at my transformation T on my first basis vector, that's T of 1, 0, 0, plugging in here, that's 1 times 2 plus 0, so that gives me 2. My second coordinate is going to be 0, my 5 times 0 plus 3 times 0, that gives me 0, and my last coordinate is 8 times z, which is 8 times 0, which is 0. I can write this out so that it looks like this form here, just so we understand the definition. So I need to write this as a linear combination of my basis vectors. So this is equal to 2 times my first basis vector, 0 times my second basis vector, and 0 times my third basis vector. And here, if I look at that, that means my first basis vector, since this is the first basis vector here, this is A11, my 2 becomes A11, and then my A21, that's times my second basis vector, this coefficient becomes my A21, and finally a n sub k, that's A31, is going to be 0 in my matrix. I do the same thing now, take the transformation on my second basis vector, that's T of 0, 1, 0. So plugging in here, I have T times 0 plus 1, so that's going to give me 1. I have 5 times 1 plus 3 times 0, so that gives me 5. And then I have 8 times z, which is 8 times 0, which is 0. Writing this out again as a linear combination of my basis vector, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 0, 1, I'm sorry. That gives me 1 for A12, 5 for A22, and 0 for A32. I now take my transformation on my last vector, basis vector, T of 0, 0, 1. That gives me 0, 3, 8. So that gives me A13, A23, and A33. So my matrix, M of T, this is the matrix that represents the transformation T, is equal to 2, 0, 0. That's my first column. This is A11, this is A21, A31. My next column is 1, 5, 0. And my last column is 0, 3, 8. And so you can use this formula here, as I have illustrated, or it's probably easier to remember that the kth column of this matrix is the operator T operating on the kth basis vector. But you have to remember, over here, you have to put it in terms of our bases. You have to rewrite this vector here, T of k, in terms of our new bases. When it's the standard bases, it's quite obvious. But if it's not the standard bases, you have to take care in this step. And we will do another simple example to illustrate this. I have written that here the kth column of our matrix is T v sub k, expressed as a linear combination of the basis vector. Here is the example when we have a different basis other than the standard basis. So I have a linear operator on F2. So T of xy equals 2x plus y, 5y. If I have my standard basis, I put T of 1, 0 in, and I get 2, 0, which is 2 times my first basis vector, plus 0 times my second basis vector. When I put T of 0, 1, my second basis vector, I get 1, 5, which is 1 times my first basis vector plus 5 times my second basis vector. So I have 2, 0 in my first column and 1, 5 in my second column. Since it's the standard basis, it's pretty easy. You could just put the 2, 0 and the 1, 5 here. But what if we have another basis? So I have the bases 1, 1 and 1, 0. We know that this is a bases because they're linearly independent since they're not scalar multiples. And once you have the right number, since the dimension is 2, once you have the right number of vectors that are linearly independent, you have a basis. So t of 1, 1. So I plug in 1 for x and 1 for y, and I get 2 plus 1, that's 3. And over here I get 5. And then t of my second basis vector, 1, 0, I plug in 1 for x and 0 for y, so I'll get 2 and then 0. But now I can't just make my matrix as 3, 5, 2, 0. I need to write these vectors, like this 3, 5, as a linear combination of my new basis vectors 1, 1 and 1, 0. So I have that work here. I have some constant times my 1, 1 plus another scalar constant times 1, 0 equals my 3, 5. This is my augmented matrix. I row reduce it so that I get x2, my second coefficient, equals -2, and x1 is equal to 5. So my vector then is 5, -2. This is basically the expression of 3, 5 in terms of my new bases. It's the new coordinate system. Again, we've changed bases from the standard bases to a new coordinate system. So this vector here, 3, 5, in our new coordinate system has coordinates 5, -2. So now I'm going to consider my next 2, 0 in terms of my new bases. Actually, it's pretty easy to see that that's just 2 times x2 and 0 times x1, which I have written here. But I went ahead and did my augmented matrix and row reduced matrix here. But this is 0, 2, which means now, using my formula, I did my t of v1 and t of v2. I write then the coefficients now, which is the 5, -2, and 0, 2. That will give me my new matrix. Now that we have these matrices, there's a goal of linear algebra that given a linear operator on V, we want to find a basis such that our matrix representation has as many zeros as possible. And our goal, our first goal, is going to be this upper triangular matrix. First, we define the diagonal of a square matrix. That's the entries along the line from the upper left corner to the bottom right corner. Then we can define the upper triangular matrix as a matrix with all the entries below the diagonal are 0, and we represent that just by putting a 0 in this lower triangular region. And then to represent that these can be non-zero, we have this wild card, the asterisk, to represent different values are possible in this upper triangular region. And now the question becomes, when can we find these triangular matrices? And we have this theorem to answer that, or partially answer that question. Conditions for an upper triangular matrix. Suppose T is a linear operator and our vectors v1, v2, vn is a basis for V. Then the following are equivalent. 1, the matrix of T with respect to our bases is upper triangular. 2, T operating on the jth basis vector is in the span of the first j basis vector, and this is true for every basis vector 1 through n. 3, the span of the first j basis vector is invariant under T for each basis vector 1 through n. We are going to do the proof that A is equivalent to B, and then we'll prove that B is equivalent to C. And by transitivity, then A will be equivalent to C. We will start with A implies B, so we're going to assume the matrix of T with respect to our basis vector is upper triangular. So assume M of T with respect to V1, V2 up to Vn is upper triangular. So it's going to have this form. We have zeros below the diagonal. The diagonal I represent with our lambda 1, lambda 2 up to lambda n. If you wanted, you could have put A11, A22 up to ANN. That might be clearer because we don't really need the lambdas for now, but this is just how I chose to do it. Then our other entries then are going to be A12, A13 up to A1n, the A23 up to A2n, and then our last is just lambda n. And I also noted that this is equal to the transformation on our first basis vector, that's our first column. Our next column is a transformation on our second basis vector, all the way up to the transformation on our nth basis vector. I can expand this out, so my TV1 looks like my lambda 1, some coefficient, and then zeros all the way down. My TV2 has my two coefficients, a1, 2, and lambda 2, and zeros all the way down. So T of Vk is equal to our k coefficients and 0 all the way down, which means my T of Vk can be written as a linear combination of my first k vectors with these coefficients, and then zeros for any basis vector greater than k. So in other words, T of Vj, and I'm sorry, here I used Vk instead of j, but T of Vj is in the span of the first j basis vector. Here I wrote T of Vk is in the span of the first k basis vectors. I'm going to make this a little bit smaller over here so we can start with B implies A now. Assume, going the other direction, that T of Vj is in the span of V1, V2 up to Vj. This is sort of the same argument, only backwards now. So T sub Vj then is equal to some coefficient times V1 plus another coefficient times V2 up to our lambda k times Vk, and then zeros for any vector beyond V sub j, which means our matrix now, because we're going to go row by row, is going to look like, well, T for V1 is going to have only our coefficient in V1, and I just renamed this A sub 1k lambda 1. Our V2 then, our second column, is going to be our two coefficients and then zeros all the way down. So we get our upper triangular matrix. Next, we'll prove that B implies C. So we're in this part of the proof. Assume from part B now that T sub Vj is in the span of the first j basis vectors. That is, T sub Vj can be written as a linear combination of the first j basis vectors. That implies T sub V1 is in the span of V1, which is contained in the span of V1, V2 up to Vn. T of V2 is in the span of V1, V2, which is contained in the span of V1 up to Vn. And T sub V sub j is in the span of V1 up to V sub j. And you can kind of see this pattern now. If we start off with, j equals 1, T of V1 stays in the span of V1. In other words, it's invariant. T of V2 stays in the span of V1, V2. In other words, if we start off in V1, V2, we stay in V1, V2. It's invariant. So T of Vj, if we start in the span of our first j vectors, our T of Vj stays in the span of the first j vectors. In other words, it's invariant. Writing that down, that is, if V is a linear combination of our first j vectors, then T of V stays in the span of our first j vectors, which by definition means the span, this subset here, is invariant under our transformation T. Going the other way, assume that the span of V1, V2 up to Vj is invariant under T. Then we want to show T of Vj is in the span of V1 up to Vj, but that's just by definition of invariant. So now we have this theorem that tells us when we can get an upper triangular matrix. And our next theorem is even better. We use this theorem to make a proof for the special case of the complex field. So when we're over the field of complex numbers, we can know that every operator has an upper triangular matrix. So suppose that V is a finite dimensional complex vector space and T is a linear operator. Then T has an upper triangular matrix with respect to some basis of V. Our proof is going to be an inductive proof, and we're going to induct on dimension of V. We start with our base case when n is equal to 1, that is, dimension of V is equal to 1. Then it's isomorphic then to R1, which is the space of real numbers, so our matrix is equal to a single coefficient, A11. Our inductive hypothesis then is if dimension of V is equal to n greater than 1, we're going to assume for all spaces with dimension less than n that T has an upper triangular matrix. Next, we'll use our inductive hypothesis to show this statement is true for vector spaces where dimension is equal to n. The first thing we know, because we're in a complex vector space, we know there's at least one eigenvalue. This is the theorem we proved earlier in our video. We are going to let lambda be our eigenvalue, and we're going to let u equal the range of t minus lambda I. Now we know that t minus lambda I is not surjective, and I have this from these two theorems first. Well, since t minus lambda I is equal to 0 if it's an eigenvalue, that means the null space has more than just the 0, which means that this is not injective. And for operators, being not injective means it's not surjective. So now t minus lambda I is not surjective, meaning the dimension of u is less than the dimension of v. And furthermore, we know u is invariant under t. So let's just take a look at why this is true. So suppose we have a vector u in our subspace u, which is the range of t minus lambda I. So that means tu is equal to t minus lambda iu. This over here is just equal to tu, and then minus lambda iu is just equal to u. So we have a minus lambda u. So we can add lambda u, and what we have is tu. So t minus lambda I u is in u, since u is the range of t minus lambda I. Also, this lambda u is also in u, since u is a subspace and it's closed under scalar multiplication, which means this whole thing, this t minus lambda iu plus lambda u, is still in u because u is a subspace and it's closed under addition, which will give us that tu is still in u. In other words, u is invariant under t. We can look at t then restricted to u, and this is an operator. We had discussed that in our last video about operators. Now, because u has dimension less than v, by the inductive hypothesis, there's a basis, u1, u2, um, of u with respect to t restricted to u that has an upper triangular matrix. And by our last theorem, conditions for an upper triangular matrix, that means if we have a matrix that's upper triangular, then t of vj is in the span of the first j vectors. So what we have then is t restricted to u of uj is in the span of the first j vectors. So here is our statement that our t of uj is in the span of our bases vectors. Well, now we can extend the spaces to a basis of v. So we're going to add other vectors from v until we have a basis. We're going to use this theorem again that we had proven earlier in this video, that operators on complex vector spaces have an eigenvalue. So here now we know for each k, t on this basis vector is going to be t minus lambda I vk. In other words, it has an eigenvalue, and then that's plus lambda k. Remember, because our t of vk is here, and then our minus lambda I vk is equal to minus lambda vk. So this statement is true. We also know that t minus lambda I vk is in u, since this is u is exactly the range of t minus lambda I. And lambda v of k is also in u, meaning t minus lambda I vk is in u, which means that this t of vk is in the span of u1, u2 up to um, and the extended bases. And according to our last theorem, and I'm sorry this is squeezed in here, that means we can expect that the matrix of t with this basis is upper triangular. And that completes our proof. We have the theorem determination of invertibility. Suppose T is in the set of linear operators over V has an upper triangular matrix, then T is invertible if and only if all entries on the diagonal of that upper triangular matrix are non-zero. And the proof is in the book. It's based on the alternate proof of the theorem we just proved over the complex field. Every operator has an upper triangular matrix. We will not do the proof in this video. We have our last theorem, determination of eigenvalues from an upper triangular matrix. Suppose T, a linear operator on V, has an upper triangular matrix with respect to some basis of V. Then the eigenvalues of T are precisely the entries on the diagonal of that upper triangular matrix. We will not do a proof, but we will do an example. Define T, a linear operator on F3, by T of x, y, z equals 2x plus y, 5y plus 3z, 8z. We've seen this example earlier in this video. The first question, which we had already solved, was what is the matrix of T? And the second question, what are the eigenvalues? When we worked this problem earlier in the video, we found the matrix by transforming a basis for F3, that was E1, E2, and E3, and then taking the transform of the basis vectors to form the columns of the matrix. So our transform on our first basis vector, 1, 0, 0, that was 2 times 1 plus 0, which is 2. For our second column, that's 5 times 0 plus 3 times 0, which is 0. And our last coordinate is 8 times 0, which is 0. So T of V1 was 2, 0, 0. That formed our first column of our matrix. TV2 was 1, 5, 0, our second column vector of our matrix. And TV3 was 0, 3, 8, our third column vector of our matrix. What this theorem here then tells us, our eigenvalues are along the diagonal. So that will be our 2, our 5, and our 8. From there, we can find our eigenvectors as we did in our last video. I will do one of them for you. I'm going to choose lambda equals 2. So we're looking at TV equals lambda v. This is our definition of the eigenvector eigenvalue. So if we subtract lambda v from both sides of the equation, we get TV minus lambda v equals 0. And then factoring out the v, we get t minus lambda I v equals 0. Plugging into our matrix now, we have across the diagonal, because we have t minus lambda I, we have 2 minus lambda, our 0, 0. For our next column, we have 1, and then 5 minus lambda, 0. And then for our last column, we have 0, 3, 8 minus lambda. And I put the 0 vector over here, our solution vectors for our augmented matrix. I plugged in lambda equals 2. So I have 0, 0, 0 on our first column, 1, 3, 0 on our second column, and 0, 3, and then 8 minus 2, 6 for our third column, and 0, 0, 0. I solved the system of equations, which is particularly easy because we're upper triangular. This 6 here gives us that V3 is equal to 0. Over here we have V2 is equal to 0. This tells us that V1 is free. So our eigenvectors are of the form V1, 0, 0. And we can check our work by taking our matrix for our transformation and multiplying V1, 0, 0, and what you see is we get 2V1, 0, 0 when we do the matrix multiplication, which is exactly 2 times our eigenvector. To review what we have covered in this video, we talked about eigenvectors and upper triangular matrices. We started by defining polynomials applied to an operator, that's polynomial P on the operator T. So suppose T is a linear operator on V, and P is a polynomial over the field F given by P of Z equals A0 plus A1Z plus A2Z squared up to AMZM for Z and F. Then the polynomial on T is equal to A0I plus A1T plus A2T squared up to AM T to the M, where we define T to the M is equal to T times T times T M times. T to the 0 is the identity operator I on V, and if T is invertible, then T to the negative M is defined as T inverse raised to the M. For existence of eigenvalues, we prove this theorem here. Operators on complex vector spaces have an eigenvalue. So every operator on a finite dimensional non-zero complex vector space, remember it does need to be complex, has an eigenvalue. From there, we went on and talked about upper triangular matrices. And we started by defining matrix of an operator M of T. Suppose T is a linear operator on V, and the vectors V1, V2 up to Vn is a basis of V. The matrix of T with respect to this basis is the n by n matrix whose entries are A sub j comma k, and they're defined as T of V of k is equal to A sub 1 k V1 plus up to A sub nk Vn. We noted to get the kth column of this matrix, we take the transformation on the kth basis vector, and then we need to express that T v sub k in terms of our bases. We also noted since this is an operator that maps from V to V, the matrices are square since V is n-dimensional and V is n-dimensional. So if no basis is specified, we assume the standard one. And with respect to different bases, we can get different matrices. So one of the goals of linear algebra is given a linear operator on V, find a basis such that our matrix of T has as many zeros as possible. In this video, our goal was an upper triangular matrix. First, we defined the diagonal of a square matrix. Those are the entries along the line from the upper left corner of the matrix to the bottom right corner of the matrix. And then we defined upper triangular matrix as a matrix with all the entries below the diagonal equal to 0. So here we have the notation for an upper triangular matrix. Our diagonal here has our lambdas. Later we'll see that this diagonal, those are going to be the eigenvalues, which is why we use lambda on the diagonal. This asterisk is the wild card. So in the upper triangle of this matrix, the other entries can be any constants. And then over here we put the 0 to represent this lower triangular portion of the matrix has all zeros. So this is our notation for upper triangular matrix. So then we have this useful theorem about when we can expect to find an upper triangular matrix. So suppose T is a linear operator on V and V1, V2 up to Vn is a basis of V. Then the following are equivalent. 1, the matrix of T with respect to our bases is upper triangular. 2, T of Vj is in the span of the first j vectors. And then 3, the span of the first j vectors is invariant under T. Then we use this theorem to prove this theorem that makes it even simpler to determine if we have an upper triangular matrix. But it is the special case that we're over the field of complex numbers. So over the field of complex numbers, every operator has an upper triangular matrix. So suppose V is a finite dimensional complex vector space and T is a linear operator, then T has an upper triangular matrix with respect to some bases of V. These last two theorems demonstrate why the work to get a upper triangular matrix makes our analysis of the transformation easier. First, we can determine invertibility. Suppose T is in the set of linear operators over V has an upper triangular matrix, then T is invertible if and only if all entries on the diagonal of the upper triangular matrix are non-zero. Second, determination of eigenvalues from an upper triangular matrix. Suppose T, a linear operator on V, has an upper triangular matrix with respect to some basis of V, then the eigenvalues of T are precisely the entries on the diagonal of that upper triangular matrix. And that's it for this video. Thank you for watching.